So now that we have our difference between average velocity and instantaneous velocity represented v bar for average velocity and just the v for instantaneous velocity, we're going to take a look at our Los Angeles trip. All right, so our Los Angeles trip, let's bring our Los Angeles trip back over here. All right, our Los Angeles trip, which has a total average velocity versus the various instantaneous velocities, including the one that got you pulled over. And what we're going to do is we're going to take this idea, this concept of our average velocity versus instantaneous velocity, and we're going to analyze it graphically. All right, so here on this graph, what you can see is that there is an axis. Our time axis is in hours. Our distance axis is in miles. This is our Los Angeles trip, but really what this is a position versus time graph. All right, and we're going to call average velocity, remember that's v bar, we're going to say that that's our solid blue line. And our instantaneous velocity, which is just v, is going to be our black line. So we're going to start by considering our instantaneous velocity. So you went on this trip, and by you I mean you. You started out traveling, and around the first hour you had this awful realization: shoot, you forgot your best pair of shoes at home. So you rush home, get your shoes, and you start heading out again. You start out and you're speeding because you wasted 2 hours driving without ever at any point in time having your shoes. So you're speeding, and then all of a sudden you hit traffic, and that traffic is slowing you down. Alright, so you're barely going at all. You're barely making any progress with a lot of time. And then finally, the road clears up. And so you just pedal to the floor. And then you get pulled over by this guy. Because, I mean, let's face it, that right there is just an unreasonable speed for you to have been traveling, Mr. Hedgehog. And after he pulls you over and he goes on his merry way, you go, holy smokes, I've got to get to LA. And you discover that there was a gummy bear between your gas pedal and the floor, and you were able to floor it even more, and you really zoom to Los Angeles. Now let's consider your final displacement compared to your initial displacement is going to be 325.52 versus 0. Alright, so here we could say your x1 was 0 kilometers and your x2 was, oh, we're doing it in miles, sorry, x0 miles, and your x2 was 352 miles. Alright, so your delta x for this is going to be 352 minus 0 equals 352 miles. Alright, so for your whole trip, your average velocity is going to be that 352 miles divided by that 5.33 hours to give you the 110 kilometers. Alright, that's the final position minus the initial position divided by the total elapsed time. That could be represented by an average velocity line just like this. This is the average of this entire trip, right? Those two lines are equivalent. If we did area, it would end up being the same. So your average velocity and your instantaneous velocity lines give you the same overall calculation of your velocity, but they're very different at different times. Here on this line, your slope is the same the whole way through, right? You have a consistent, smooth, steady slope. But here, your slope is positive and not as steep here. And then it's negative and equally unsteep, right? Your slope here, your rise over your run here, would give you the slope for this time juncture for 1 hour. And here your rise over your run would give you the slope for this section. Alright, and then here your slope up here would give you a more steep slope here. And this is a very shallow slope here. Alright, and so the slope at any one point is going to give you your instantaneous velocity, right? The change in x over the change in t, and your instantaneous velocity is over a very small point, right? It's anywhere that you can find a straight, smooth line, right? That slope would give you the instantaneous velocity. However, none of these points, if you calculated the slope of any of these segments of the graph, none of them would be the same as the average velocity. But if we ended up comparing them all and putting them all together, normalizing them, then you'd have the average. And so this is one way to take a look at graphically how an average velocity is compared to an instantaneous velocity. And we could actually describe how the average velocity is different than the instantaneous velocity because some points are steeper, some points are shallower, some points are nearly zero, you have zero slope, some points are negative, but overall, right, your average velocity for the two is the same.